Hi, grade fours. So remembering that we've been talking about four types of motion today, we're talking about linear, rotary, oscillating, and reciprocating motion. I thought I would bring in a guest speaker today. Some of you may remember Mr. Eriksen from the days where he came and visited for Genius Hour Club. He is a systems engineer who also happens to be my dad, and he's going to help us to look at some examples of those four types of motion today. So hi, Mr. Dad / Mr. Eriksen. So what
All
can you
right.
show us about linear, rotating, oscillating, or reciprocating motion?
Okay. Let's try a couple of examples of the covers, because most things are a mixture, right? When you're on a bicycle, your feet are going up and down. So that's the same as a reciprocal. You're going up and down. So that's your reciprocating, right? But the gear that you're pedaling is rotating. So that is your rotary motion, right? It's going around. So it turns the shaft, which then, because of the wheel, rolls you forward, which is your linear motion. So you reciprocated with your feet up and down. The wheel rotated because of that reciprocating motion, right? Because that's all I just did. And because it's sitting on the ground, took you forward and back, right? So, and that's what happens with a lot of different examples, right? So I happen to be using here a screw drill, and if I put it inside something, now if I put this in water or powder and I turn that, the stuff will move up the shaft from the rotary motion, giving me a linear motion. Or if I put water, then it would turn the screw, and that's how we get our electricity, right? As the water goes down the turbine and it spins it. So
Yeah,
that's a
so
rotary
remembering that
motion.
with Niagara Falls, grade fours, the water comes over the falls, obviously, and hits what's called a water turbine. So a water turbine is like a big gear. It looks a little bit different because it needs to be able to capture the water, and that's how we turn the falling water, the action of the falling water, into electricity by using then a gear, which spins because the water keeps falling on it, and then that helps to turn a motor.
Right. And to get it so that it makes a lot of electricity, the water can't go as quickly as we want it to go for the mechanical, so we would have more gears sitting on that shaft that was rotating, and that would be a big wheel to a little wheel, and that would make the rotary motion of one turning the other one, making this one, the big one, would make this little one turn very fast, because it's many turns of this one to go around that other one.
Yeah, so remember in gear ratios, when we talked about gear ratios using our spur gears and bevel gears, the number of teeth in the larger gear divided by the number of teeth in the smaller gear will tell us our gear ratio. And a higher gear ratio means that that big wheel turns with a lot more force, and the little wheel has to turn a lot quicker. So what are some other examples of linear, rotating, or oscillating, or reciprocating gears?
Well, you've got your steering wheel in your car. You're turning the steering wheel, which is turning a shaft. And on the end of the shaft, we would have a gear. And that gear, as it turns, moves around a rack. And that would move the wheel so that, let's say, I'm turning now to the left, or I'm turning to the right. And that moves the wheels of your car, right? So now that is a linear motion going back and forth that's rotating your tires. So it's kind of confusing. The tires are doing this, but the rack is going back and forth. And what's nice with the rack is it doesn't slip. When you stop, it holds that position very strong. So if you're steering a straight path, you're making little, boy, things are dropping all over on me.
So it doesn't slip like your demonstration.
That's right. It holds the position, and now I want to turn a little to the right, I rotate, and it moves that little bit more.
So in this case, the wheel or the pinion in our rack and pinion gear, the pinion rotates, so it's rotary motion, and the rack part is linear motion, so it moves back and forth. And then remembering also from our lesson, the linear motion means that it moves left or right or up or down, and it becomes a reciprocating motion or an oscillating motion when it goes back and forth repeatedly. So an oscillating motion would be more like the ticking of a pendulum or a clock, where it goes in an arc, and reciprocating motion is back and forth in a straight line repeatedly.
The other way to think of it too, see, like let's say this is a gear in here, and what's it doing? It's moving the tape out, which would be our rack, and back in again.
So in this case also we have two forms of motion. We have the linear motion of the actual tape being pulled out and the rotary motion inside the mechanism of the tape measure.
That's right. Okay.
Awesome.
And and you can measure things, because if your gear is very fine, then when you're rotating it, the screw will move, or your rack will move a very accurate amount, and you know how much it moved to hit something, or to when it opened up, and now you've measured something, saying, well, it's so many turns till it's open, so many turns till it's closed. And now you know how many rotations equals, whether it's an inch, a centimeter, or something.
And you had a vice grip there also, right?
I was having a vice, yeah, and I had it here.
So again, in a vice grip, we have a couple of different types of motion. So when you turn the handle on the vice, that's our rotary motion. Then it looks like a big worm gear because it's like a screw, right?
Right, and the screw is held here by effectively like a nut, and then as it's turning, see how it's closing, and it has phenomenal strength. I can do lots of turns here. If I left my finger in there, it would get flattened.
So the amount of effort that you have to put into turning that wheel or turning the gear at the end is very little compared to the amount of pinching force at the end of the vise, obviously, because that would be strong enough to hold two pieces of wood or metal together for a project.
That's right. And it's, again, how much strength I have is whether I'm using the shaft closer or further. The further out, the more fulcrum I have, or the more force I'm able to put onto that screw, and therefore how much more I can put into the squeezing action in the vise.
Well, thank you for helping us to demonstrate this today. This has been very helpful and lovely to see another face in our social distancing lesson planning.
Yeah, we're all still here. We're just at the end of the cameras.
The joys of FaceTime. Well, thank you for joining me for our lesson today, and we'll talk soon.
Take care.
Bye.
Another day. Bye-bye.